Hey guys, my name is Nilesh and I'll be making a series of videos regarding generative adversarial network. This series of video is for anyone, those who are new to artificial intelligence or machine learning as in such, and those who want to explore about another aspect of machine learning which is also known as unsupervised learning. So I'll be teaching you how you can make your first GAN and let's see how it goes. I hope you enjoyed this video, and if you are new to the channel, make sure you like and subscribe and also share the videos. So let's get started. Alright, so the first thing that we're gonna see is what are generative networks. So basically, according to a definition, I think we should go to Wikipedia first and then we see. So a generative model or a generative adversarial network is a class of machine learning systems invented by Ian Goodfellow and his colleague in 2014. The two neural networks contest each other in a game, in a sense of game theory. Given a training set, the technique learns to generate new data with same statistics as the training set. For example, train on a photograph, GAN train on a photograph can generate new photograph that looks at least superficially authentic to human observer, having many realistic characteristics. Alright, so what I can say is this. Let's go to Google Draw. Yeah, Google Draw. So imagine this guy. So imagine this. Uh, it says that there are two types of network. One network is a generative network, and the other network is a discriminator, okay, or adversarial network. What happens? Let's color these two different. So let's say this is red, and the generative network is green. So what happens, guys? That we tend to we tend to generate random noises from the generative network such that a discriminator actually tries to verify whether the photographs that were generated from the generator is actually fake or real. Alright, so the work of a generator is to generate random noises, and the work of a discriminator is to validate or recognize or discriminate whether the generated input is true or fake, real or fake. All right. So I'll give the links in the description below about uh, the Wikipedia about the Wikipedia article, and also the people those who invented the adversarial network. Okay. So here are those people. Ian Goodfellow was a lead author. So you can find his profile on the internet. He's currently working with Apple. He used to work with Google, and now he's currently working with Apple. And Yeshua Benjoy is one of the, you can say, godfathers of AI, along with Jeffrey Hilton and Ian LeCun. So I think these people, you should tend to search throughout the internet if you're really interested to see how artificial intelligence came into the way they are right now. Okay, so these are some of the articles that I'll be sending, and this is overview how Google has represented it. So you see there is real data, okay, and then this generated data basically tries to generate random noises, and in time the generated random noises tends to generate uh, data which actually looks like the real data, and then the discriminator suggests whether the discriminated data is the generated data is real or fake. If it is fake, then the loss functions try to come closer to each other, right? If it's making sense to you. All right, so this is very simple model. You can see that there are real images, and there are also there are generated images as well. Okay, so again, the real images are trained and the random inputs are given. So the real images are trained, and the discriminator says whether it is a real image or a fake image. I think once we start building it, it will be much more clearer for you to understand how this thing works. So for now, just know that there are two types of network: a generator and a discriminator. And what happens is generator generates random noises, based upon the real data, and the discriminators discriminates or separates or decides whether the data generated by the generator is real or fake. Okay, so let's get started and see how far we can build with this intuition of generating two networks. All right, so a lot of statistics will come. This is the probability. This machine learning is based mostly in probability. So let's see how we can create this probabilistic model and see how far we can go with it. All right, so let's get started. So I'll be using same Google Colab generator. I think spelling is Cerebral Network. All right, let's get connected and let's see what are the things we can actually see in generative adversarial network. So we know this, right? So both the generator and discriminator are neural network. The generator output is connected directly to the discriminator input. So yes, generator output will be connected to discriminator input. Through backward propagation, the discriminator classification provides signal that the generator uses to update its weight. So through backward propagation, the discriminator classification provides signal that generator uses to update its weight. Let's go and look at the discriminator. The discriminator is a in a GAN is simply a classifier. It tries to distinguish real data from the data created by the generator. It could use any network architecture appropriate to the type of data it's classifying. Okay. Let's see about the generator. Generator learns to take fake data by incorporating feedback from the discriminator. It learns to make discriminator classify its output as real. The generator training requires higher integration between the generator and the discriminator than discriminator training requires. So random input and blah 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 blah. Okay, okay. So let's get started. I think we'll be using MS dataset for the same. So what I'll do is I'll just import some basic. So let's say from TensorFlow import keras and import numpy. This will mostly be used to generate random noises, and then we also need to import matplotlib as well to visualize as pyplot. And let's run this, and the data that we'll be using will be from keras dataset mist of load dataset load data, yeah. So this is a type of unsupervised learning, so we actually okay, so this is a type of unsupervised learning, so we actually don't need our, our labels. So the idea here is that the machine itself will generate appropriate label for itself, and then it will do the rest of the training and classification and stuff like that. So here's the thing. So now we have imported or downloaded the data. Now what we can do is we have to create something known as a latent space. Now the idea of a latent space is basically that it will try to reduce the images into a lower dimension, you know, convert the pictures uh, into lower dimensional basically, like uh, principal component analysis. If you're familiar with the term, it tries to reduce the data into from a higher dimension to a lower dimension, right? If the data is in 3 dimension, you can reduce it to a dimension less than 3. I hope that's making sense. So that's what we are going to do here. So we'll create will create a latent space which is basically 100. Okay, now you need you also need to do what you also need to do is that you need to convert the X string into a range between, in previous videos, if you're doing image classification, supervised learning image classification, then you need to convert it into a range from 0 to 1, right? But in supervised in sorry in generative adversarial network, you have to convert it to -1, from -1 to 1. Okay, so the numbers should be distributed from -1 to 1. But before that, guys, I just want to show you how what is the scaling of the whole thing. So I'll just do it for 10 images, 1 to 10, and I want to show you how the scaling looks like before we actually dig into the transformation. So pld.plot, and then I think this makes sense. We reshape it. Yeah, so the numbers are ranging from 0 to 255. Let's see what happens when we uh, normalize it or scale it. So before that, let's write scaling. So after scaling, let's see. I will also do the same for y test as well. Let's see, so let's copy the same thing in the shell below. Yeah, so the images are converted from -1 to 1. All right. One of the reason of doing this is because we are putting it into a latent space, right? A space, as like copying something, taking data from the original, like taking data from the original, taking the original data set, and then just throwing it randomly into a latent space. So we need some sort of, height, so that when we throw our data into a particular page, the data should spread out nicely. Even if it is trying to cluster, it has a lot of space to decide where to settle down. So that's why we are doing. So think this whole thing as taking the original data, you know, unstructuring it and just throwing it randomly into a canvas. Okay, so the smaller the canvas, the more problematic it becomes for you, because the data might go off the grid as well. In this case, what we are trying to do is we're making sure that the canvas is not too big and not too small as well, but also but of appropriate size, where when we throw you know the data point on the canvas, it will remain, you know I mean, just to say that it will remain, most of the point will remain in the canvas itself. Okay, so that's the reason why we do it in this fashion, just giving a little bit of length from last time. If you're doing, normal image classification, you tend to do it from 0 to 1, but here in this case we are just giving it a negative number as well. All right, so moving on, now since we have done this, the next thing that we can do is create a network. All right, so we can create a network, generate so we can create a generator basically. Okay, so we can create a generator and let's see how it goes. Okay, so the dimension, so image data basically says that it is 28 into 28, so 28 by 28 pixels. All right, and then what we can do is we can initialize, we can write a variable in it, and then we can say keras dot initialize it, And what we are going to initialize is a random normal. All right, so we'll be creating a so so we are generating some sort of tensors. Okay, so just some tensors which are basically normally distributed. If you know a bell curve, so it is normally distributed. So the standard deviation that we are looking for is, let's say, if you want to keep it normal, you can keep it normal. I'll just go for 0.1, for example. Let's see, let's keep it lower and see what happens. Okay, so standard deviation 0.1 means it is closer to 0. All right, so let's see what happens next. So uh, once we have the initializer, what we can do is we can create a network generator. So we'll be using sequential model again, model, or I can write generator. So we'll be using sequential model again. So keras dot model dot sequential, and then I hope this is visible. Let's make it bigger. Okay. So then we will write the first layer. I think I'll make it small. All right, guys. All right, guys. So we have created our Alright guys, so we have created our generator and we can see the summary of our model. Let's see how it works, how it looks like. So this is the summary of the model. And if you want to see the architecture as well, what you can do is you can write keras.utils, and from there you can write model plot model, and then you can pass your generator the name of the model, and the file name you can, let's say, write generator.png, and shapes, uh, show shapes, and we write true. Let's see how it looks like. So guys, this is our model. So that's it guys for the first video. So this is how a generator is being made, and few of the things that I like to point out over here is, number one, that you do whenever you're doing scaling for GAN, make sure it is from -1 to 1, so the numbers are distributed from -1 to 1. Secondly, you don't need a label data set. You just need the input. I mean, you just need the distribution, right? If I'm making any sense to you, you don't need the y. You just need the features. All right. You don't need the target variables. You just need the independent variables. Okay. If it makes sense to you, you just need the independent variable. In our case, we only need our x's. Also, the generator tends to generate images in a latent space. Like I said before, you have to make sure that you create a latent space. In this case, it is 10. You can obviously go for a higher number as well, but make sure the latent space or the latent dimension that you are creating is less than the number over here. Okay, so you can either go for 100 or 200 as well. It does not matter. But all you need to make sure that the latent space is less than the space. So this will be a higher dimension and this will be your lower dimension. Okay, and also the random numbers that will be initiated, you have to make sure that it has standard deviation of 0.01. Okay, so this is also one of the things that you have to uh, make sure. The standard deviation should be less, like for example it should not be 2. If you do it for 2, the the output will be very pathetic. So make sure you do it for numbers like 0.01 or 0.02, and then you can create your own latent space. So I've started with 128 because I found that 128 gives me better results. So I started with 128 neurons. The next layer is just the double of the previous layer. You can add a third layer as well, but I mean the fourth layer as well. I just kept it simple, and yeah, that's it. So one more thing, the activation function in this case will be relu, leaky relu, and the output of the generator will be the activation function of the last layer. The output layer will be tan h. Okay. So this is it for this video. So in the next video, we'll try to create a discriminator, and after that, we will see how we can follow it up. Okay. So hope you enjoyed this video, guys. If you did enjoy it, make sure you like and subscribe, and also share this video with your friends as well. Okay. So thank you, guys. Hope you guys enjoyed it, and see you in the next one.